Hello Israel, it's me, Seven Heaven, coming to you once again with another video. I have no rights to the video or music. It's strictly for educational purposes only. Let's listen to them beyond discovery speak about Cern and the portals and their so-called hydrogen collider. Let's get into it, Israel.
Shutdown for extensive upgrades and maintenance, the renowned Large Hadron Collider, LHC, at Cern, situated near Geneva in Switzerland, roared back to life in April 2022. This momentous event marked the initiation of an extraordinary scientific endeavor known as Run 3, which promises a series of mind-boggling experiments scheduled to captivate the world's attention until 2024. However, Cern has recently made another unsettling announcement concerning the activation of the famous Large Hadron Collider. Join us as we discover the astonishing potential threats this groundbreaking development brings to our very existence. The largest and highest energy particle collider was built by Cern between 1998 and 2008 in collaboration with more than 10,000 scientists and hundreds of universities and laboratories from more than 100 countries. It is built in a tunnel having a circumference of 27 kilometers. It lies around 175 meters beneath the France-Switzerland border near Geneva. The first ever collision in this Hadron Collider was achieved in 2010 at an energy of 3.5 tera-electron volts per beam. This is almost 4 times the previous world record. After the upgrades, it reached 6.5 tera-electron volts per beam. The collider consists of 4 crossing points where the accelerated particles collide. Each one of these 7 detectors is designed to detect different phenomena and is positioned around the crossing points. The Large Hadron Collider primarily collides proton beams, but it is also able to accelerate beams of heavy ions. Lead-lead collisions and proton-lead collisions are typically performed for 1 month annually. The main purpose of this collider is to allow physicists to test the predictions of various particle physics theories. Most importantly, they are trying to measure the properties of the Higgs boson and search for the large family of new particles predicted by supersymmetric theories. The term hadron refers to subatomic composite particles made of quarks held together by a strong force, analogous to the way that atoms and molecules are held together by the electromagnetic force. The commonly...
So I'm learning that Cern is a company that put together that thing that they call hydrogen collider. It's trying to open up a portal using some of their antimatter, which I don't believe they have a lot of, to be able to go back to heaven, a war with the Most High angels. I have said this before, but we all know Israel, Most High is not letting that happen. I don't even know if they're, or believe, if they're able to even travel through portals. We know it's different realms, but as far as trying to get back up there, it's never gonna happen.
known hadrons include baryons like protons and neutrons. These hadrons also include mesons like the pion and kaon that were first discovered during cosmic ray experiments in the late 1940s and early 1950s. A collider is a kind of particle accelerator that brings 2 opposing particle beams together so that the particles collide. These colliders may be difficult to construct, but in the field of particle physics, these are incredibly powerful research tools as they reach much higher center of mass energy than the fixed target setups. Scientists can then analyze the byproducts of these collisions that provide us with evidence and information about the structure of the subatomic world and the laws of nature that govern it. Quite a few of these byproducts are produced only by high-energy collisions. They decay after very short periods of time. This means it's not possible to study these in any other way. The collider is contained in a circular tunnel at a depth ranging from 50 to 175 meters underground. This variation in depth was intentional, meant to reduce the amount of tunnel that lies under the Jura Mountains so as to avoid the need for excavation of a vertical access shaft there.
Okay guys, I'm going to show you how I got this awesome high-tech smartwatch for free. I'm not even kidding.
This particular tunnel was chosen so that Cern wouldn't have to spend huge amounts of money purchasing expensive land on the surface. This would also impact the landscape. An added benefit was the shielding against background radiation that the Earth's crust provides. The 3.8-meter wide tunnel is lined with concrete and was constructed between 1983 and 1988. It was previously used to house the Large Electron-Positron Collider. This tunnel crosses the border between Switzerland and France at 4 points. While most of it lies in France, the building above ground holds ancillary equipment like compressors, ventilation equipment, control electronics, and refrigeration plants. The data produced by LHC and LHC-related simulations were estimated at about 15 petabytes per year. The computing grid was built as part of the LHC, designed to handle these massive amounts of data obtained from its collisions. It is an international collaborative project that consists of a grid-based computer network infrastructure. The construction section of the Large Hadron Collider cost around 7.5 billion euros. It is one of the most expensive scientific instruments ever built. Its construction was approved in 1995 with a budget of 2.6 billion euros and another 210 million euros for the experiments. After going operational on the 10th of September 2008, the initial testing of the LHC was delayed for 14 months when a magnet quench incident caused extensive damage to more than 50 superconducting magnets, their mountings, and the vacuum pipe. During the first run from 2010 to 2013, the LHC collided with two opposing particle beams of either protons up to 4 tera-electron volts or lead nuclei. The first run discoveries of LHC included the Higgs boson, numerous composite particles, including the bottomonium state, and the first creation of quark-gluon plasma. The initial focus of research by the Large Hadron Collider was to investigate the possible existence of the Higgs boson, a vital part of the standard model of physics that was predicted by theory but hadn't been observed previously because of its high mass and elusive nature. The scientists at Cern speculated that if the standard model was correct, the LHC would produce several Higgs bosons every minute. This would allow physicists to finally confirm or disprove the existence of the Higgs boson. Besides that, the Large Hadron Collider allowed scientists to search for supersymmetric particles and other hypothetical particles. After the inaugural tests in 2008, the first operational run lasted between 2009 and 2013, after which there was a long shutdown for upgrades that lasted until 2015. The second operational run occurred between 2015 and 2018, after which there was another long shutdown until 2022. In April 2022, the LHC became operational again with a new maximum beam energy of 6.8 TeV. This round is expected to last until
Seems to me that the hydrogen collider keep malfunctioning, breaking down. Could it be the Most High is not letting it work, Israel? Or could it be just something that's malfunctioning and just not seem to work? Make you think.
2026. During this third run of the Large Hadron Collider, scientists were left baffled when on July 7th, a crack appeared in the magnetic field of Earth. This mysterious crack wasn't something that occurred like a lightning flash. It wasn't short-lived. In fact, the crack in Earth's magnetic field remained open for a good 14 hours. This enabled the intense solar winds to stream through the opening and cause huge geomagnetic storms that created some incredibly mesmerizing auroras. Science fiction enthusiasts were pretty excited to learn about this. Some even went as far as to suggest that maybe Vecna, the monstrous villain from Stranger Things, might have crawled out into our world through this crack. That's just a die-hard fan's dream that will never come true, sadly. But the geomagnetic storm stirred by this crack did create an aurora so beautiful it was difficult to take our eyes off it. But how exactly did this crack appear? Well, as it turns out, this crack in the magnetic field was formed because of a rare phenomenon called a co-rotating interaction region from the Sun, or CIR. These CIRs are actually large-scale plasma structures that are generated in the low and middle latitude regions of the heliosphere when the fast and slow-moving streams of solar wind interact with each other. The heliosphere is the region surrounding the Sun that includes the solar magnetic field and the solar wind. Just like coronal mass ejections, or CMEs, the co-rotating interaction regions get flung out from the Sun toward the Earth. These can contain shock waves and compressed magnetic fields that cause stormy space weather that usually presents itself to us as magnificent aurorae. This particular one hit the Earth's magnet during the early hours of July 7th and produced a long-lasting G1 class geomagnetic storm. According to the National Oceanic and Atmospheric Administration, or NOAA analysts, a coronal mass ejection was embedded in the solar wind ahead of the co-rotating interaction region. So should we be concerned about this crack? Well, according to experts, this is nothing to worry about, as such cracks in the magnetic field of Earth are pretty normal. This magnetic field acts as a shield that protects us from solar storms hurled our way by the sun. It is believed that the numerous cracks in the field open and close relatively quickly, but these recent cracks have...
Now we know the magnetic field that's protecting the Earth, our flat Earth, is weakening because of the solar storms that we're getting, or they say we're getting. What do you think, Israel?
proven that they are capable of remaining open for several hours at a time. Harold Freya, lead author of a study on this discovery back in 2003, said, "We've discovered that our magnetic shield is drafty, like a house with a window stuck open during a storm. This house deflects most of the storm, but the couch is ruined. Similarly, a magnetic shield takes the brunt of space storms, but some energy slips through its cracks, sometimes enough to cause problems with satellites, radio communications, and power systems. But thankfully, there weren't any radio blackouts or power outages associated with this crack opening up in the magnetic field. However, the residents of Canada and the US were treated to some mind-blowing northern lights. And scientists have also revealed that the sun is heading up toward its most active period in the solar cycle. It is already unusually active much earlier than expected. This means that your chances of spotting an aurora, which are pretty good even now, will only improve over the next 3 years."
Nick Fury, it would appear you're not dead after all.
Got that right. Now streaming, Nick Fury returns to the sea.
This crack in the magnetic field of Earth isn't the only thing the Large Hadron Collider has discovered recently. Back in July 2017, multiple analyses based on the large data set collected in 2016 were revealed to the public. The Higgs boson's properties were studied in more detail, and the precision of several other results was also improved. Since March 2021, the LHC Collider experiments have discovered about 59 new hadrons in the data collected from the first 2 runs of the collider. On July 5th, 2022, it was reported that a new type of pentaquark made up of a charm quark, a charm antiquark, an up, a down, and a strange quark was observed while analyzing the decays of charged B mesons. Every particle physics experiment eventually begins to suffer from diminishing results after a few years of running. Since the prime results reachable by the device begin to be completed in the later years, proportionally lesser results are seen. The simpler way to deal with this is to upgrade the devices involved, especially in collision energy luminosity and improved detectors. Along with a possible increase to 14 tera-electron volts collision energy, a luminosity upgrade of the Large Hadron Collider, referred to as the High Luminosity Large Hadron Collider, began in June 2018. This upgrade aims to increase the luminosity of the machine in order to improve the chances of visualizing rare processes and improving statistically marginal measurements. The third run is being considered an intermediate stage in the Large Hadron Collider program. The major highlight of the first run was the discovery of the long-anticipated Higgs boson, the primary achievement. The second run included the discoveries of the major decay modes of the Higgs boson, verifying that this particle is indeed the origin of mass, at least for all the relatively heavier known elementary particles. Cern is hoping that the new third run, planned to end in late 2025, will double the current LHC dataset. According to Cern sources, this third run will most probably be followed by a longer period of preparation that could extend through 2029. By then, the fully grown LHC will once again burst into action with a rate of collisions 10 times larger than the current one. The fourth run will estimatedly last until 2042, and this one will gather the ultimate data set, almost 10 times larger than is expected at the end of Run 3. The key to LHC physics is the accumulation of massive amounts of recording of proton-proton collisions for analysis. Proton is their particle of choice. as it's the easiest one to handle and manipulate, so it can be accelerated to the highest energies. However, it isn't an elementary particle. It is a bound state of quarks that are held together by particles called gluons, which are the quanta of the strong nuclear force. In order to better understand the collisions at LHC, we can think of the proton as a bag of jelly beans that contains quarks, gluons, antiquarks, and even heavier particles like the W and Z bosons that are the quanta of the weak interactions responsible for radioactive decay. When two protons collide, the most likely result is that the two bags full of jelly beans will be ripped apart and spill out particles that will reform into protons, pions, and other more familiar particles. But sometimes, only two quarks or gluons tend to collide head-on. This compresses all of their energy into a tiny spot, and then releases it back to the quarks and gluons, or maybe to the heavier known and unknown particles too. Physicists can get a glimpse of the laws of nature at incredibly short distances by studying and analyzing these extremely rare reactions, causing a tremendous energy release. As the Large Hadron Collider accumulates data, these experiments will keep building up, thereby obtaining larger and larger samples of these rare reactions. Experts are hoping that they will eventually accumulate enough events to provide irrefutable evidence of a discovery. Now, finding these occasional hard collisions is a huge data challenge. Bunches of protons tend to collide 40 million times per second in the Large Hadron Collider. Each of these bunch collisions has at least 50 or more individual proton-proton collisions. The photographic evidence of these collisions captured by the major LHC detectors, ATLAS and CMS, is then written into permanent storage. Each of these pictures is nearly 20 times larger than a typical smartphone photo. This means keeping all the evidence for just 1 second of operation would produce a 1,000,000 gigabyte database. However, in every second of data obtained, the majority of the 40 million events are simple and familiar ones, with just a few thousand W boson events and only one Higgs boson event that is buried in this stream. Therefore, one of the key components of each LHC experiment is the trigger, which is a bank of computer processors that select a few hundred per second of these collisions for the permanent record that will be analyzed by physicists. Despite the immensely selective approach, the LHC experiments already constitute one of the largest computed databases in the world. The primary goal of the LHC now is to discover new elementary particles that could provide evidence for new, still undiscovered fundamental interactions. Some of these new proposed particles could be heavy and would decay into clusters of quarks and leptons, displaying very high energy. Scientists, however, don't think any such particle would be discovered in Run 3 at best. These experiments might provide some interesting statistical hints and maybe some suggestive event pictures with the novel features. This will get the theorists talking. The High Luminosity Large Hadron Collider in Run 4 and more few runs is expected to confirm these suggestions. Right now, there is a real opportunity in searches for weakly coupled new particles like the ones predicted in models of dark matter. Reactions producing such particles tend to have low rates as they are not produced by the strong interactions, but instead by the weak and electromagnetic interactions. Therefore, any increase in the dataset could prove helpful. The dark matter particle interacts too weakly to leave a signal in the Large Hadron Collider detectors. This is not an issue as one can look for visible particles recoiling against the invisible emissions in accordance with Newton's third law. But in a lot of the models, the partners of dark matter particles release very little amounts of visible energy, which leads to minimal recoil signals that are not recognized by the triggers of the experiment. The trigger improvements in Run 3 are expected to improve the coverage for such subtle signals, and the increased rate will help reduce a sample of rarer events in which the recoiling particles are pushed out into easier view. The improvement will greatly enhance the ability of ATLAS and CMS to recognize these signals. And that's not all. Cern also has multiple preliminary designs for a future circular collider. It is going to be the most powerful particle smasher ever built, and its construction will probably cost between 9 and 21 billion euros. Although at the moment, not everyone is convinced that the future circular collider is a good investment. Sabine Hosenfelder, a theoretical physicist at the Frankfurt Institute of Advanced Studies, Germany, has stated there is no reason to think that there should be new physics in the energy regime that such a collider would reach. The large sums involved could be better spent on other huge facilities, like placing a major radio telescope on the far side of the moon, or a gravitational wave detector in orbit. Both would be safer bets than a new collider, considering the fact that the LHC is yet to finish its third run and then get ready for a fourth one, both of which will contribute more than enough to particle physics for the time being. And like all the big science projects, LHC is advancing slowly, but it's also providing us access to deeply buried knowledge that was unattainable previously. Run 3 is the next stage of this process, and physicists are expecting it to bring forth quite a few surprises, like the recent crack in the magnetic field of Earth that remained open for several hours.
Wear wigs? Got to be Flash Glue Remover. Doesn't damage your scalp, and it's made with aloe vera and castor oil.
Much love, Israel.